Hi, in this video, we will solve the heat and wave PD equation. You must master the technique to solve the 1D heat equation. So this is the example. In this heat equation, we want to find the temperature distribution with respect to the x location and also the time. Initial and boundary condition will be given together with the PD here in order to find the particular solution. So this is your end. You want to find the particular solution for this PDE. So far, you have learned that the separation of variable method assume that the solution for PDE is equal to the multiplication of the function x and y here, where x, y are the independent variables. In this PDE, the independent variables are x and t. Therefore, we need to change this into x and t. So this is the solution that you assume for this heat equation. And we can simplify the symbol here equal to capital X and capital T. So if you differentiate u with respect to t, so in this case you obtain x t prime minus with c squared, where the c squared is your constant, and then differentiate u with respect to the x twice, then you obtain x double prime t equal to 0. So you can rearrange this equation in such a way that you separate the variable t on one side and variable x on another side. So you let this equal to a separation constant negative lambda. Lambda is an unknown, therefore we can assume it to be 0, negative value or positive value, where the alpha here must be greater than 0. So for the first case, after you solve these two PDE, from the first ODE here, this term equal to negative lambda, then you can obtain the solution for t. When the lambda is equal to 0, you obtain t1. When lambda equal to negative alpha square, you obtain your t2. Similarly, when lambda equal to positive alpha square, you obtain the solution for t3. Repeat the same procedure for the second ODE. So you obtain the solution x1, x2, x3 for these three cases. Then you need to multiply the t and x for each cases to obtain the general PDE solution. Repeat the same procedure, you obtain the general PDE solution for the second case, which is equal to t2 multiplied with x2. And your general PDE solution for the third case is equal to t3 multiplied x3. These are the items that you have learned so far. In the next step, we are going to apply the initial and boundary condition in order to find the particular solution. To obtain the particular solution, you need to understand the concept for the eigenvalue and eigenfunction. Let's recall the eigenvalue and eigenvector that you have obtained in the ODE cases previously. For example, in this case, we have a two-mass spring system, and we want to study what is the response for the mass 1 and response for the mass 2 here. The equation of motion that describes the motion of these two mass spring systems is given here. Since we know that the x1, x2 will be oscillate in sinusoidal wave over the time, therefore we can assume the x1, x2 is equal to the sinusoidal function here, where the a1 and a2 here are the amplitude for the x1, x2, and then omega is the frequency of the oscillation. Theta here is the initial phase information. If you differentiate the x1, x2 twice, then you obtain the x double dot 1 and x double dot 2 to be negative omega square x1 and x2. Substitute the x1, x2 as well as the x double dot 1 inside here, then you can obtain the first equation to be this term multiplied with x1 plus this term multiplied with x2 equal to 0. So this is your first equation. Repeat the same procedure by substitute the x1, x2 and the x double dot 2 inside here. Then you obtain this term multiplied with x1 plus this term multiplied with x2 will be equal to 0. So this is your second equation. There is a correction here, this will be mass 2. And you success to arrange the equation 1 and 2 in the matrix format here. With that, we success to rearrange the equation in this format, where you can see lambda is the eigenvalue of this matrix that describes the characteristic for this mass spring system. For example, let us assume the mass 1, mass 2 here equal to 40 kg, K1, K2, K3 here is equal to 200 Newton per meter. Substitute this information inside the matrix here, then you should be able to obtain this equation. You should have learned this before. To find the eigenvalue for this system, which is equal to the omega square, since we know that x1, x2 solution cannot be equal to 0, because the x1 and x2 are vibrating in the sinusoidal function format, therefore they cannot be 0. If the x1, x2 cannot be equal to 0, to satisfy this equation, the determinant for this matrix must be equal to 0. Since we know that lambda is equal to omega square, so you can substitute inside these two terms to obtain the lambda. And then you perform the determinant by multiply these two terms, which give you this, and minus with the negative 5 multiplied with negative 5. So after you expand and simplify this, you should be able to obtain this equation. Then you can solve the lambda where you factor it. You obtain the lambda minus 5 and lambda minus 15. So you success to obtain the eigenvalue to be 5 and 15. And we assign the number for it. So for the lambda 1, which is the first eigenvalue, we use the lowest number, followed by the next larger number. So this is the common practice to arrange the eigenvalue in ascending order. So you success to obtain the eigenvalue from the mass spring system here. One of the important function or application for the eigenvalue is to review the characteristic of the system. For the two spring mass system or the vibration problem, the main characteristic of this system will be the natural frequency. You should have learned the vibration at this frequency will give you the maximum amplitude. So you can see the lambda here is linked to the omega square, where the omega is the natural frequency for this vibration system. So you can continue to find the natural frequency from the eigenvalue. With that, you success to find the first natural frequency for the vibration system equal to square root 5, second natural frequency equal to square root 15. Be careful, eigenvalue is not equal to the natural frequency. Many people find the eigenvalue and assume that this is the natural frequency for the mechanical system here. So this is wrong. In fact, the eigenvalue is just the root for this characteristic equation that consists of the characteristic information, such as the natural frequency. So in this case, your eigenvalue, which is the lambda, is linked to the characteristic information in omega squared. So we can further find the natural frequency to be square root of lambda. So these are the two main difference. Eigenvalue is lambda, but natural frequency is omega. So you obtain the first natural frequency and first eigenvalue to be this value at mode 1. Second natural frequency and second eigenvalue at mode 2. So there is a correction here, this will be 2. In engineering application, we use the term mode to indicate the first and second characteristic that you obtain. So now you should be able to obtain the eigenvalue at a particular mode. Then you need to substitute the eigenvalue inside and solve the solution here. So this solution is called the eigenvector. For example, in the first mode, substitute the omega equal to square root 5 inside here. Then you should be able to obtain this equation. So you can expand this matrix into two equations here by taking the 5 multiplied with x1 minus with 5 multiplied with x2 to give you 0. And then you continue with second equation, negative 5 multiplied x1 plus 5 multiplied x2, which give you 0. Then you can proceed with either one of these equations. Just take the first equation, rearrange it, you should obtain x1 equal to x2. If you rearrange the second equation, you will obtain the same answer. You can set x1 to be any value. For simplicity, we just let the x1 equal to 1. Substitute inside, you obtain your x2 equal to 1. Therefore, you obtain the eigenvector at the first mode to be 1, 1. It means that at the first mode, or the first natural frequency, the maximum vibration at max 1 and max 2 will be at 1, 1 respectively. Remember, the x1 here can be any value. So if you put it to be negative 1, then you obtain your x2 equal to negative 1 as well. So this is also correct. So what is the meaning for the eigenvalue here? In this example, the eigenvector actually tell you the shape at a particular mode, which is called as the mode shape. At mode 1, you success to obtain the eigenvalue to be this. Natural frequency at mode 1 equal to square root 5 and the eigenvector equal to plus minus 1, 1. The eigenvector tell the shape of the vibration for mass 1 and mass 2 at the mode 1. So you can see the vibration for mass 1 and mass 2 change over the time here. So at mode 1, the natural frequency is square root 5 and you can proceed to find the period, which is equal to 1 over f, and we know that the omega is equal to 2 pi f. Therefore, you obtain 2 pi divided by omega. Substitute the omega equal to square root 5 inside, then you obtain the period equal to around 2.81 seconds. Therefore, you can see that from the original position to one full cycle here, it takes 2.81 seconds, which is the period. The red color is the vibration for the mass 1 and the green color here is the vibration for mass 2. The eigenvector here tells us that when the mass spring system here is vibrate with square root 5 radian per second, then the shape or the vibration pattern will be in this format. Let this to be the equilibrium position for the mass 1 and mass 2. So we can see that at this particular time here, let's say at t equal to 0, when the x1 equal to 1, then the x2 equal to 1 here as well. So you can see that these two mass is moving one to the right hand side. Then the mass 1 and mass 2 are vibrate in such a format here over the time. At this particular time at half period, then you see the vibration is on the left hand side, which gives you the negative 1 on x1 and x2. Then the mass keep vibrate, and at the full period here, you get back the x1, x2 at 1 here, which means it is moving to the right by 1. In simple, if you give the eigenvalue in 1, 1, or if you give the eigenvalue in negative 1, negative 1, both of them are correct. This is because for the first eigenvector here, when the mass 1 is moved by 1 to the right hand side, then the mass 2 will move 1 to the right hand side as well. So you can imagine the vibration pattern like this for these two mass, which is in phase. The mass 1, mass 2 move up and down together. If you present the eigenvector in this answer, it means the mass 1 will move to the left by -1, and your mass 2 will move to the left by -1 as well. So you can imagine the vibration pattern for these two mass to be like this, where you can see both of them move left and right together, which is in phase. Therefore, we can say that these two eigenvectors are correct because they give us the same mode shape, where the mode shape or the vibration pattern at this natural frequency is in phase. In simple, we find the eigenvector because we want to know the mode shape for this mechanical system. Mode shape tells you the shape of the vibration when the mass spring system here is vibrate at this frequency. So this is the natural frequency, therefore this vibration is at its maximum amplitude. As you can see, the eigenvector here is an unscaled value. It can be represented by either ±11 or ±55 and so on. Like you take the eigenvector, multiply with any constant m, let's say. So this eigenvector is still considered correct because they will give you the vibration pattern or mode shape to be the same. All of these eigenvector format are correct because they give us the same mode shape, which is unique, regardless of the different scale. If you want to have unique shape as well as unique scale, then you need to perform the normalization to obtain this normalized eigenvector. You need to take the previous eigenvector here and divide with the corresponding magnitude, and then you obtain the scale eigenvector or the normalized eigenvector here. Previously, you have the eigenvector equal to ±11 here. So let's scale this eigenvector. You need to divide with the magnitude. So the magnitude is obtained by square root 1 square plus 1 square. So after you perform the calculation, you should obtain this answer. You can also present the eigenvector in this format, which gives you the same unique shape. Let's normalize this eigenvector by divide it with the magnitude. So the magnitude can be computed by square root 5 square plus 5 square. So after you compute this, you should obtain the same eigenvector here. So this eigenvector is called the normalized eigenvector, which gives you not only the unique shape but also unique scale. From the normalized eigenvector, it's easy to tell that these two eigenvectors give you the same mode shape. Therefore, in many engineering applications, we prefer to represent the eigenvector value in the normalized format. We have completed the discussion for the eigenvector for mode 1. Let's continue for the mode 2 here. Substitute the natural frequency equal to square root 15 inside here. We should be able to obtain this equation. So this will be the mode 2. Expand this matrix, we obtain -5x1 minus with 5x2, which is equal to 0. For the second equation, you have -5x1, -5x2, which is the same. So from here, you can rearrange to obtain your x1, which is equal to -x2. Let the x1 equal to 1, then in this case, your x2 is equal to -1. Therefore, this is the eigenvector for second mode. For the second mode here, you have the natural frequency equal to square root 15 and the eigenvector or the mode shape at mode 2 equal to 1 and -1. Similarly, you can find the period for mode 2, which is equal to 2 pi divided with square root 15, which gives you around 1.62 seconds. Therefore, you can see that the vibration for one period here will be equal to 1.62 seconds. From the eigenvector, when the x1 here is moving to the right by 1, and then your x2 will move to the left by -1. Therefore, you can imagine the motion of these two mass is out of the phase over the time. As you can see over this picture, at time equal to 0 here, you can see when x1 moves to the left by -1 here, then the next two move to the right by 1. So they are always out of the phase. Let's say at this timing, t equal to 0.81 seconds. So when your x1 is moved to the right by 1, your x2 is moved to the left by -1. Similar to at time equal to 1.6 here, they are moving out of phase to each other. In this example, you success to find the eigenvalue and eigenvector for a mass spring system. And you success to find the natural frequency from the eigenvalue, which is an important characteristic for the dynamic system here. Also, you success to interpret the mode shape from the eigenvector that you obtain, and you success to visualize the vibration pattern at the first natural frequency and the vibration pattern at the second natural frequency. So the mode shape for the first natural frequency here is in phase, and the second natural frequency here is out of the phase. At mode 2, the natural frequency is higher than mode 1, therefore you can see that the oscillation here is faster compared to mode 1. Now you should have better understanding what is eigenvalue and what is eigenvector. Now we are going to discuss what is the linkage of eigenvalue and eigenvector to the eigenfunction. In general, the eigenfunction is the solution to differential equation. For example, from this mass spring system, you success to obtain the eigenvalue problem here. And you solve this problem to obtain the eigenvalue mode 1 and mode 2 and eigenvector for mode 1 and mode 2. Our main interest will be to find what is the vibration x1 and x2 here. So this solution basically is equal to the superposition of the eigenfunction. You can see that eigenfunction 1 here consists of the eigenvector, which is the amplitude, multiplied with the sine omega t plus phase 1, where the omega 1 here is equal to the square root eigenvalue 1. In fact, this is the eigenfunction for this ODE, which consists of the eigenvector information as well as the eigenvalue information. Similarly, the eigenfunction 2 here is comprised of the eigenvector 2 and square root of the eigenvalue 2. This is equal to your second natural frequency. Eigenfunction here is the solution to this ODE problem. To prove the eigenfunction 1 is the solution to this ODE problem, let us substitute all the information for eigenvector 1 inside and the natural frequency 1 inside. You have the x1 equal to 1 multiplied with sine term here, therefore we can substitute the x1 here to be this value. You have x2 equal to 1 multiplied with sine term here, then you can substitute the x2 equal to this sine term here minus with the same thing here, therefore you obtain 0 here. So this term can be eliminated, therefore you only have -200 multiplied with the sine term. So this is the answer on the left hand side. On the left hand side, you need to obtain the 40 multiplied with the second derivative of x1. So since your x1 is equal to sine term here, after you differentiate twice, then you should obtain x double dot 1 equal to -5 sine square root 5t plus phase 1. Substitute the x double dot 1 inside here, then you obtain this answer. Calculate it, you should obtain the final answer to be -200 sine term. And if you compare the LHX, which is the left hand side with the right hand side here, then you see these two answers are the same. You can repeat the same procedure by substitute the eigenfunction 1 inside the second equation here. So you can substitute x1, x2 as well as the x double dot 2 from here. After you substitute, you should be able to obtain left hand side equal to right hand side as well. Therefore, it's proven that the eigenfunction 1, which is this answer, is the solution to this ODE. You can substitute the eigenvector for the second mode and the natural frequency for the second mode here to form the eigenfunction 2. And then you differentiate twice to obtain the x double dot 1 and x double dot 2. After that, you substitute this information inside this equation to check the left hand side and right hand side information. So by doing this, you should obtain the left hand side equal to right hand side, which proves that the eigenfunction 2 here is one of the solutions to this ODE. Now you should have better understanding on the eigenfunction 1 and 2 here, which is just the solution to this ODE that is consists of the eigenvector, mode 1, mode 2, and natural frequency, mode 1 and mode 2 here. To find the total solution, we can just use the linear superposition by taking the summation of all the eigenfunctions, which is multiplied with a constant. So, bear in your mind, the eigenfunction is just the solution to a given differential equation. In this case, you have the ODE. So, the eigenfunction is the solution to this ODE, which is consists of the eigenvalue and eigenvector, which is shown in this example.